We have a mailing list. Now we have a couple of hundreds people. I don't know exactly the number, but if you want to spread some information, send us an email and ask to forward it. So you can send an email to fdf@cern.ch, and then obviously after a little bit of moderation, we will forward it. And last thing, we have this series of seminar. Roughly every couple of months, we hold one of these seminars. More or less, they are taken from people that submitted abstracts to the conference, to the FDF meeting at CERN. Okay, so we will record this seminar to publish it on our YouTube channel, and I'm reading now that we are also live on YouTube as we speak. So does this mean that I don't need to record it, Davide?
No, record it nevertheless. Just to I don't know if the live streaming will be kept after the meeting.
Okay, perfect. So let me introduce today's speakers. So we have two speakers today. So the talk is going to be given in collaboration between Luca Colombini and Andrea Abba. So Luca has a background in microelectronics. His degree is from the University of Pisa in Italy. He's senior staff engineer at CAEN SPA. Designs of electronics boards, focus on FPGA firmware development plus embedded software. And he's responsible for the open FPGA implementation and development to customers, support for customer during solution exploration and adoption. And Andrea Abba is a PhD from the Politecnico di Milano, where he lectured until 2015. During his academic tenure, he participated in several INFN experiments, that's the Institute for Nuclear Physics in Italy, notably contributing to the development of a trigger system for the LHCb experiment at CERN. In 2013, together with two partners, he founded Nuclear Instruments, a company specializing in innovative solutions for particle physics, astrophysics, and aerospace applications. He currently serves as CTO at Nuclear Instruments, focusing on firmware and software development. So I'll start the recording now. You can share your screen. It's good that we have the screen share before I start the recording for the YouTube video. Are you sharing this already and I can see it?
Luca, your microphone is switched off. I see you that you're talking. Okay.
Okay, I can see the screen, and so I'll mute myself and start the record.
Hi, everyone.
Luca and Andrea, the floor is yours.
Yeah. Hello, everyone, and welcome to this webinar. Sorry for not showing the presentation. I was waiting for 1 hour with the presentation ready to show, and then at the right moment it was not on. But anyway, okay. So let's start with this seminar about. The title is Innovative FPGA Customization Tools for High-Speed Data Processing in Physics Experiments. We are Luca Colombini, me and Andrea Abba. We work for two different companies, but we work mainly together to develop either hardware and software solution for physics experiments. And the focus today is on FPGA customization. So it's what kind and Nuclear Instruments in collaboration offers to the market to customize the board we produce to get results that are not the one that you could get out with off-the-shelf boards with their normal firmware that is provided when you buy the board. You see in the slide the number of products we build and sell with different specifications, but really they are all digitized boards, so they convert analog signals into digital one to be processed later on for any further processing that may be needed. And some of them is also a logic unit, so a board with an FPGA. All these boards have an FPGA as the main building block, and some is a logic unit that can provide different input processing input signals, digital input signals that provide output digital signals. So for us, the FPGA customization is translated in a name which is OpenFPGA, and I will explain what we mean by OpenFPGA in the context of KINE and nuclear instruments solutions. So we have this large portfolio of boards. These boards are not OEM; they are not sold to be assembled in other modules. They are not building blocks for other things. In the sense, they are not development boards, but they are complete tested boards, production-ready boards, with a possibility to customize the FPGA firmware by the end customer, by the person that buys the board and can design its own piece of firmware inside of it. The customization of the firmware is performed by using a software which is called Psi Compiler, which is a proprietary tool, and along with it, it has a graphical user interface and it has a graphical entry mode, and then you can translate to VHDL or HDL code, and then you can use FPGA vendor tools, standard tools for the target FPGA. Mainly now for us is Xilinx, but in the past and some of the modules still have Altera. And so you can use local compilation flow, so you can locally install these tools and build your own firmware locally, or you can leverage on the remote customization service on a cloud platform that is provided by us, which is called the MyKINE Cloud Solution Platform. A brief introduction to the group, to the KINE group, and to the nuclear instruments, just to have an overview for those of you that doesn't know about us. So the KINE group has been built. The KINE company has been built and founded in 1979 as a spin-off of the Italian Institute for Physics, INFN. And the core business is electronic instrumentation for physics experiments. It is not limited to that just now, because as you can see, there's been a lot of spin-off activities, ranging from spectroscopy vision to radio frequency identification to other divisions that works on the security, and the KINE house works on synchrotrons control. And we are a number of 160 about people working in mainly in the region Italy and some others in other places. Maybe I can give the word to Andrea to introduce its own company, which is Nuclear Instruments.
Yes, Nuclear Instruments, it's a company of about 21 designers. So while KN it's focused on design and production, Nuclear Instruments is mainly focused on design. We make some custom applications, so we produce custom hardware, but just for custom design, while we realized on the collaboration of KN for the design and distribution of catalog product. So our core business is the design of readout front end, but not only, we also work a lot with groups that need customization in design of detectors, so detector module, front end amplifiers, digitalization, and so on. We work, as I said, mainly in physics and astrophysics design, but also for some space missions. Now, at the moment, we are designing the payload for 2 satellites that will be launched in the next 2-3 years. Okay, thank you. So, Nicole.
Okay, I continue a little bit with the presentation. Then Andrea will talk more deeply about the Psycompiler tool and will make a demonstration of its usage and its in the implementation of firmware on real hardware. So the solution for the FPGA digitizers and the Psycompiler firmware generator is illustrated here. You can see a screenshot of a PC running Psycompiler on the right. And you can see there is a graphical user interface and number of blocks that represents the functionalities you want to implement. And on the left, you see the number of boards you can build firmware on. Just for an example, this is one of the families of boards we produce and we sell. This is called Digitizer 2.0 modules, meaning that in the past, the legacy digitizer called 1.0 are still in production, still are sold, but they didn't support the open FPGA approach. At least you have to sign an NDA to work on the firmware on that. Now with Digitizer 2.0 and other modules, you can use the open FPGA approach without signing any NDA. For example, this family of boards has a number of different mix of number of channels and sample rates. For example, you can see ranging from large number of channels, 64 with 125 megacycles per second at 16 bits, up to 16 channels with 1 gigasamples per second, 14 bits in the module that is going out now in production, which is the one that has the largest sample rate up to now, but there are modules in development which has even more sampling rate than this one. And this is a matrix that shows the combination of sampling rates and number of bits and the form factor for all of our products. So you can see there are boards in VME standard, in desktop standard. It's not a standard anyway. You can use desktop modules on your own desk or rackable in a rack. And the one that I was saying before, development is ongoing for even for a 5 gigasamples per second platform based on the RF SoC from Silence FPGAs. So they integrate in one chip, one system on chip. Very fast sampling rate. You can generate signals and have a larger number. In this case, the number of channels, as you can see, differentiated between different versions, but it's 8 channels, 5 gigasamples per second, for example. Maybe Andrea, I don't know if he wants to add, it is the main designer of the board. And one of the implementation, and Andrea knows much more than me about this. It is the implementation of trapezoidal filters, which is the main building block to process exponential decay signals from detector in physics experiments, which can be implemented at 5 gigahertz on this kind of boards. I don't know if Andrea wants to add some more, but
Yes, not only the trapezoidal, but also we have the QDC, PSD based on both peak on area or the ratio between the area and area. You can imagine how it is difficult to manage a system that produces 5 gigasamples per second on several channels. With PsyCompiler, we see later that is really simple because all the backend works of making this parallel algorithm is done by us, and so you just can focus on the design of the algorithm without have to understand how to operate with a filter that is designed to be serial, but we make parallel to operate at 5 gigasamples per second. Just that.
Okay, so let's dive into the OpenFPGA approaches for our digitizers. The mainstream approach is by using an FPGA platform, a digitizer, or anyway, not only digitizers, but also logic units, which is another piece of the puzzle, plus PsyCompiler. This is the mainstream approach. On some of the platforms, on the 27 Digitizer 2 platforms, you can use VHDL, Verilog design entry with HDL flow by using a firmware development kit, okay? But this is a solution, this is only disclosure on request to specific customers who want to use this approach, mainly for larger experiments, not only, but anyway, you must discuss with us to enter this path. Anyway, in general, the digitizer boards, we talk about digitizer boards in this case, have two different flavors for what we call the framework. The FPGA approach, we'll show you later, will give you the possibility to customize a user module which is embedded in the design, but it is surrounded by a framework which is designed by us, tested by us, and this framework can come in two flavors. One is the scope flavor, which is for what is in physics is called trigger mode. So you want to have a single source of trigger that triggers every channel collects data at the same time. And this is possible only on the Digitizer 2 platform. Otherwise, all other modules can have a DPP flavor, which means each channel can trigger independently on whatever you want to use as a trigger, mainly discrimination, but not only. And you can store short samples of waveform along with the information which you can extract from the pulse, and this is called in physics streaming mode. Okay, so you can see from this small picture, small design, that the customer firmware is just one piece embedded in the FPGA. You have an interface inside the FPGA where you can place your logic, and the rest of the logic is the framework, which is designed by us. And then the custom firmware can sense the digital inputs, can drive digital outputs, and receive ADC data in input to be processed and can generate events towards the framework. Same concept in a different picture, in the sense that the framework can assess the user logic through configuration. In the case of science design, for example, we use XC for light register access. You have one interface to configure your user registers, and the user logic can generate streaming of data out output, and we provide all the support and the management of the memory, the ADC, the DAC, the I/O, which is a complex task to do if you want to design your own board. And we have done it before, so we provide it to you, ready to use. And okay, we provide the infrastructure. You can implement your algorithm for data processing, parameter extraction, and trigger logic. And the SciCompiler is the graphical tool that with precompiled modules, so you don't have to write your own code because the code has been already written. You assemble the logical modules together. And the things that SciCompilers do is to translate that design into an HDL logic that you can put in your user space and interact with the rest of the system. At this point, I think Andrea can illustrate better than me the SciCompiler, which is a tool that's been developed by Nuclear Instruments, and Andrea is the main designer of the tool, so it is the right person to explain.
Okay, so in brief, SciCompiler is just a visual programming language. So you can make a block diagram. You can see a block diagram in SciCompiler on the left in this slide. And then this is what is the user experience. It just pick blocks, IPs from a catalog, put in an hierarchical design, connect the block each other to implement the functionality required, and then press compile. And what happens? It happens that these functional blocks are converted in a firmware. It means that we brought the VHDL or the HLS that is behind this block, and the tool just pick from the catalog this block and instantiate the different component, create the signals, and connect everything together. Which is the output of SciCompiler? First of all, it is a Vivado project. So it is an open source system because even if the software itself is not open source, the output is open source. So you can you physically have the encrypted Vivado project on your computer if you locally compile, and you can access to the file, see the VHDL generated by SciCompiler, and because it is a tool that just merge the IPs that has been designed by hand, the output is not like the Vivado HLS output that is almost impossible to understand, but it's really clear and easy to read. And then the tool can automatically convert, invoking Vivado, this firmware in bitstream to be programmed on the digitizer. Also, the tool manages the testing, as we can see, because it is possible to make a simulation and debugging in real time of the firmware. So, Luca, may you go? Okay. The idea is that you can take one of the digitizer, any of the digitizer, design your block diagram, and SciCompiler will create the product. It's important to understand that you can migrate from one device to another device. So the design, you focus on just on the algorithm. The hardware platform is just like where to implement the design. But you can have multiple more or less channel. You can have a higher or less sampling frequency. But any design can be run on one hardware or on another hardware. And all this without knowing anything about VHDL or Verilog. We have entire experiment. For example, at the European Spallation Source, there are like 7 detectors, several analyses that are completely based on SciCompiler firmware. And people that design this firmware has almost any capabilities to write code in VHDL. So this enables the scientist to design directly the firmware in the way that they would communicate directly with the people, the electronics group that maybe should code their algorithm. Change. Next. Okay, which is difference between SciCompiler and, for example, tool like LabVIEW. Let SciCompiler implement firmware that works inside the FPGA directly in the DAQ of the instrument. So it can exploit full parallelism of the FPGA because you are not implementing a CPU that makes some calculation, but you are designing the data path and the data pipeline of the processing algorithm. And moreover, it has a much lower latency, for example, in control systems that use our new digitizer that has also analog out. On the other side, obviously, LabVIEW tool, it's more easy to be used and more has more maybe advanced functionalities, including graphics functionalities, but it works on the CPU of the computer, and so it is it has a higher latency and also can relies only on the power of computational power of the computer. We have now it's written 100 or more virtual blocks that are very similar to instrumentation that you can find in your lab. So we have, for example, oscilloscope. We have a filter to calculate the energy that can be, for example, trapezoidal filter or charge integration or shapers and so on. We have TDC. Mainly the block that we offer are divided in input-output block, in processing block, logic blocks, and in readout blocks. This is just an impact slide that show the catalog updated to few years ago, so now it's much more than this. User pick one of the more of these blocks put in the design, we will see later, and the build engine convert this in before a Vivado project and then in a bitstream file. Next. SciCompiler, it's three tools. SciCompiler itself that generate the firmware. Resource Explorer, that is a debug tool to interact directly with the hardware and make a first visual readout of the hardware. And the last is SciSDK, that is the tool to write the readout using it's a library at the end to make the to make application that read out a SciCompiler firmware. Next. As I said, the Resource Explorer is a powerful tool, very easy to be used. It just enumerates everything you put inside your firmware, a register, an oscilloscope, a logic analyzer, a list, or a spectrum, and so on. And then you can like set a register, read a counter, reset a counter, or view a waveform, and so on. This without writing any line of code. As soon as you upload the firmware on the FPGA, this tool can run also directly inside the device. Next slide, and it is able to create a visual environmental where you can probe values or set register or make statistics, analysis, and so on. SciSDK, on the other side, is a more complex tool that allows the readout of any firmware developed with SciCompiler, but in several programming languages. You can have a look that we support almost all new programming language. Moreover, the library is portable on Windows, Linux, but also on embedded devices like Raspberry Pi, and works inside Jupyter Lab, for example. Install in Python, for example, is really easy. You can just pip install SciSDK and immediately work. And it also works inside LabVIEW because you can, for example, develop the firmware in SciCompiler, the part that run in real time in SciCompiler, and that make maybe slow control and data visualization in LabVIEW if you're used to use LabVIEW. Next. SciCompiler has integrated the simulation, so we can replace some or all input of the design with some stimulus. We have an integrated stimulus generator, and then we can probe any internal signal. To generate stimulus, we have a full detector emulator inside, so we can generate a realistic spectra or realistic signal shape, or we can load file that maybe you can dump with digitizer or oscilloscope. And then we can also script the access, for example, to register or procedure that involve the readout of something in the firmware in order to simulate interaction with the readout libraries. The output is then visualized on a common tool that is GTK Wave integrated inside compiler, and this tool can also plot analog signals, and you can analyze the output of the simulation in a very easy and convenient way. What we can do, for example, this is the first one is with compiler. The first one is an application where we can reconstruct the interaction point of neutrons on position sensor straw tubes. The second one is the calculation in real time of our FFT that can also be used for trigger, because we have the FFT that is directly calculated in hardware, and so we can, for example, trigger the acquisition when a specific frequency appears in the signal. We can make time-of-flight spectroscopy, like with the high-resolution multi-channel TDC inside the design. We can make, obviously, pulsate analysis with different kind of filter. We can convert any complex logic. For example, we have a board, Luca maybe has not said before, but we have a board that is the V2495, that is a fully digital board with some 100 channels, input-output channels, that can be used to reduce several racks of DIMM crate in a single board that implements maybe trigger, counting logic, and so on. And it's a valid solution to upgrade maybe old experiment that has very old electronics that maybe will die in the short future. Implementing, for example, a pulsate analysis is extremely simple. We can use a trigger connected to a trapezoidal filter, connected to a energy sample, and to a spectrum. This replace a standard digitizer, or better, replace an old analog shaper with peak holder and peak sampling ADC. The advantage in having a compiler is that also you can reconfigure on flight any parameter inside the firmware. If they are registered, you can just access with SciSDK or Resource Explorer and change it. But even if they are firmware, it is possible to remote reprogram any of our board, even via Ethernet. And so even if the board is not possible to reach the board physically, you can change anything in the firmware on flight. Some few other example in this slide. You can implement any kind of filter with finite or infinite impulse response. You can make a trigonometric operation. We have full floating point support inside the tool, and you can have a tool that make, for example, real-time statistics analysis like real-time variance, real-time average, standard deviation, and so on.
At this point, I just say something about the FDK, which is the approach in the case you have a large base of HDL code already.
You're mute, Luca.
Okay, you're muted, yes.
Oh, sorry. Okay, just my turn to illustrate a little bit about the FDK approach. The FDK approach is just in case you have a large HDL code base, or you are an experienced FPGA designer and you want to dive into writing code and not having a different approach. So the FDK approach gives you the same possibilities, but you are the access to the user logic is through an HDL interface with a predefined interface, documented interface, and the code you write inside your block is just any kind of block code, HDL generated by HLS or whatever tools generates HDL code, and you only have to comply with the interface. It is not much readable, probably the slide, but this is the snapshot of the snippet of the interface. And okay. The approach is the same. You can have this approach of FDK on the Digitizer 2.0 platforms, and you have access to the data from the ADC, and you can generate events towards the processing and sending the data to a remote host. And you can implement your own trigger logic and trigger stamping as well. And you get signals to synchronize multiple boards together. This is an example of the Digitizer 2.0 platform with the possibilities of its communication interfaces, which can be 10 gigabit Ethernet either in TCP or UDP. With UDP, you get a much higher bandwidth but you have to manage the possible loss of data and otherwise, you can have a 1 gigabit version of the firmware, and the USB interface is always there, mainly for local interfacing, debugging, and web interfacing. But anyway, you can use both of the interfaces at the same time. And the VME in this case, what is a VME, but this is just for legacy. We use it for power supply and not much more at the present. And another possibilities that is given to you by using the PsyCompiler or the FDK, mainly for the PsyCompiler, you can remote customize your FPGA. You can send your customization to the kind cloud, and you can so you don't need to have your FPGA tool installed locally. In the majority of cases, the Digitizer 2.0 has needs a local installation, but you don't need to perform the full flow of the design. You only synthesize at least locally in case of Digitizer 2. Otherwise, you send the code to the cloud platform, and we send you back the programming file for your board. So you can then upload it to the board and test it. And that's the flow you can use with the remote customization service. At this point, I think we have finished with the slides, with the presentation. We have prepared a small demonstration of the platform. I asked the organizers if we have time to do a 10 minutes presentation at this point.
Yes, of course, go on.
Okay, so
We finish at 4 in the UK, so 5 there. So you have 20 minutes.
I will try to be quick, just to give a reference for people that are curious to see what can do with PsyCompiler and where to find documentation. There is a site that is dedicated to PsyCompiler, that is PsyCompiler, psy-compiler.com. Here you can find, okay, just a presentation there. Very important. We have under resources, hands-on lab, several lab organized to in argument. So you see the tag with the different argument, and all the labs are well explained with maybe some mathematical background about what you are doing. For example, I don't know, simulation on how to make a baseline restorer is there are simulation results, some information how to implement it, and a repository with the code for each of the experience that we propose. We have a forum where it can possible to ask questions, and also there is a dedicated area that is the My PsyCompiler area. That is where you can find all your compilation, your project, if you decided to archive on the cloud, and also it is possible to have a look to design directly from the web, or access to the compilation report. And for example, as Luca said, we can build online. We can access to a particular build. We can have the history like on JIT of your project, and you can have the artifact for each of the build, and you can see the logs for each build, and the FPGA usage and statistics on timing issue and so on for each build. This is for the online part of the design. About the software, this is the the software, you have here the introductory page. We can create a new project, for example. What I will make a very simple demo. We don't stay here waiting that compile. We have already the result loaded, but I will start from scratch so you can understand how it's easy to make it. We want to make a charge integration. So I create a new project. Okay, I have just to choose the board. We have several boards supported by CyCompiler. We can choose, for example, the SciSDK, that is the development kit. I can choose a folder where to save CERN QDC is the name of the project I'm creating. So I create my project. Now, okay, I have this blank page. Now we create everything in a single page, but it is possible to create sub-page, some component, and also reuse component between different design. In any case, I can, what I want to do is take a signal, trigger on the signal, calculate the baseline and calculate the charge integration, and then have a look to the signal and make the spectrum. So first of all, I need the signal. I right-click on toolbar and select the board pin, and I choose analog input. In analog input, this board has two channels, A0 and then A1. We choose just A0. Okay, and this is our input for the A0. Now I need to trigger on A0. So I go again in toolbar and I choose under trigger. I have several kinds of trigger. Now I choose the simplest, that is the trigger leading edge with hysteresis. I enable the hysteresis. This is the property of the IP core. It's very similar to the property of Vivado. The trigger has just few properties, just the size of the signal in input, and if I want or not to compile the hysteresis module inside. And then I can connect the input with the data in. I have several modes to represent the link. My prefer is this one. Then I can choose the polarity. I don't know, how can I choose the value of the polarity? If I click on the block, I have here on the left a real-time view of the help of the block that explain before the theory and the IOs. For example, input, I see that is I is the positive polarity. So I can right-click on the polarity and create a constant and set to 1 to say that I want a positive polarity. And then I need a threshold. Threshold, I want to program it. So I can create a register. So I can right-click on threshold, choose fan out pin to register, and just press new, because automatically it set the size of the register to the correct value in number of bits. And then I connect the threshold. Delta, it's the hysteresis value I can put as a constant, so I can choose a value that is big enough to do not have too much noise when the trigger goes down, when the exponential goes down. So I can choose 16. Now I can move this design whenever I want, and I can add the baseline restorer now. So I can right-click on the toolbar and choose under signal analysis baseline restorer. Here I set how many memory I want to reserve to the baseline restorer, so I can choose 1000. I connect the output of the trigger analog signal to the input of the baseline restorer, and also the trigger is required for the baseline restorer, because you know when you want to calculate the baseline, you want to avoid that the baseline enter the signal enter in the baseline. So I need the trigger to know when there is the baseline. And then the mlen is the length of the baseline, and all this, how long the baseline restorer should hold the baseline when it has a trigger. These two parameters I would like to have register. So I can right-click and select register, new, and add this. And the same for the hold. Okay. So now, if to calculate the QDC, I need the QDC module. So I can do with accumulator and other stuff, but an easier way is to just right-click here, toolbar, signal analysis, QDC. Here it asks me how many bits it has the QDC, how long I want the pre-trigger. This is used for the memory allocation, and then how many bits I want the output of the QDC. Just 16, it's fine. Again, I can connect the signal to the output of the trigger to the output of the trigger, And then I need the baseline signal. So I connect the baseline to the baseline. We have the zoom. Then there are a few registers I can use to configure the QDC, like how many samples I want to integrate in the QDC. So I right click on integration sample and choose fan out to register. And then I can set the pre-trigger. So I right click on pre-trigger input, so how many trigger I want to integrate before the QDC start. And I create another register. And then again, because the QDC produces a number that is bigger than the input, because you accumulate multiple numbers. So it is by default shifted by 16-bit. And so the gains allows to choose in fixed point how many bits you want in the result. And so I choose gain and I create another register for the gain. Okay, now if I want to make a spectrum, the output charge is my output of the charge integration, and the output data valid is when the charge integration is completed. So I can right click on toolbar and choose DRQ. In DRQ, we have all readout modules. You have to the histogram, is simple histogram, imaging module, oscilloscope, digitizer, anything we want. We can choose, for example, spectrum. Here I can choose how many channels I want on the spectrum, 4,000. How is large each bin of the spectrum, 24 bits, for example. And then I can connect the charge to the input of the histogram and the strobe to the data valid. So each time I have a new event, so I have a strobe on the data valid, I will have an event on the spectrum. Now, in a very simple way, if I want to just see the input signal, I can right-click on toolbar, or again in DRQ, and choose oscilloscope. Oscilloscope behaves like a real oscilloscope. I can choose how many channels I want, up to 128, and how many samples I want to acquire in the window. Then I can decimate to simulate the nanosecond per division trimmer on the oscilloscope. So I can choose, for example, 4,000 samples. Okay, and now I can, for example, connect the output of the monitor of the QDC, that is just the input delayed by the pre-trigger, to the analog input. So I can see the analog input. Then I want to see the trigger. I can connect the trigger signal to the first digital track. Each analog input has 4 digital tracks in the oscilloscope. I want to see when the baseline is old. I can connect the baseline old to the second, sorry, this is the old time. Running and not old is this one. So the signal tell me when the baseline is in old and when the baseline is running, okay? And then if I want to see when I'm integrating, I can connect the integration monitor to another digital probe. And if I want to see when the integration is completed, I can connect the data valid to the last probe. Okay, this is everything you need to make a very simple project that take the analog inputs, trigger on the signal, calculate in real time the baseline when we are outside the pulses, calculate the QDC, make a spectrum, and also make allow you to see the data on an oscilloscope to see the input signal and trim parameter like the trigger or like the integration length. We took in total for 5 minutes. So if I would write this code in VHDL, starting from scratch, writing also the readout, because in these 5 minutes, we designed everything from the configuration of the ADC to the USB readout. I don't know, you can see the hardware. This is the hardware we target. This is the very small evaluation kit of PsyCompiler. But it is very simple. But if I would write the USB support in the FPGA, the driver in for the Windows, the library to read out the data, and so on, I would take at least, I think, a couple of days. But we did it in 5 minutes or less. Now, the next step is just to ask the tool to assign an address to all the register and the oscilloscope and the spectrum module. It's very simple. You can just write auto-assign address, and then you can execute the compiling, for example, or local or on the cloud. On the cloud, I can just press start compiling, it says your project does not exist on the server. Do you want to create it? You write yes. You can write a simple QDC demo. Then and this create the project, and now it make a commit, because every time you can make a new commit like on Git. So I can choose it to keep the source code on SciCompiler cloud or not. So I can confirm I want to keep code there. And now it started to create the project. So this part is executed on your computer. It's SciCompiler that is converting the block design in a Vivado project. Next part, when it becomes black, it's executed on the server. Now we just need to wait that the server becomes ready. It is executed on the server and generate the bit stream for you. This is a really advantage to use the server, because because an installation of Vivado, it's like to be between 80 and 200 gigabyte, while the installation of just SciCompiler, it's a few about a couple of gigabytes. So now Vivado started. We just keep the part that we wait that Vivado generate the firmware. You can see that we have a stream directly from our server to your computer to see the log of Vivado output directly on your screen. So you can even intercept error and so on. The same is true if you compile locally. If you compile locally, we do not receive anything about your project. Then when you finish to compile your design, you can open Resource Explorer. That is this tool I already opened. You can, first of all, load the firmware on the board using the bootloader. Then I'm generating with a signal generator, the kind detector emulator. This tool is generating this spectrum. I can reset. So this generator is a statistical generator. It generates random pulses that follow the statistic that we program. It's quite big. I can try to move the computer. It's difficult to see. But if you look on internet, it's the DT58110B, and it is generating signal in input of the device. So Resource Explorer enumerate everything is inside our design. So the register, the oscilloscope, the spectrum, and so on. And we can set the parameter of, for example, of the trigger. For example, now the trigger is trimmed correctly. You can see the trigger here on the oscilloscope on blue that we are correctly trigger on the signal. But if we reduce the trigger, for example, to 1000, we see that we have no more trigger. No more trigger mean also that we have no more data valid signal, so we are no more integrating the signal. In fact, if I look at the integrator it's to 0. Now, if I set the trigger, you see the integrator that integrates the values of the charge. Integrate for the period, the signal is green is high, okay? And when it finishes, it generates the strobe signal to make the spectrum. In fact, if I reset the spectrum and I start again the acquisition, you can see that we have these two peaks that is growing up. If I change, for example, the gain register to 3000, you will see that the spectrum changed the position because we are changing the gain.
Sorry, Andrea, but we wanted to have the possibility for some questions at the end.
Yes,
it's
I finished.
Okay.
This is the end. Okay. That's all. Thank you.
Okay. Thank you, Andrea. Thank you, Luca. Anybody has any questions? I know that probably people have to go at the end of the hour, but let me stop the recording and please raise your hand if you have a question. Davide?
Hi, Luca. Hi, Andrea. Very nice presentation.
Thank you.
I'm curious about how this tool interact with Git. I mean, I think so far, and at least in the demonstration, Andrea showed us how to create the project, everything with the graphic interface. But let's say that I want to have like a continuous integration to test all my changes that I want. Is there a way to
Yes.
create a script and
It's possible. We do it for testing, for our testing. It's let me say not yet released, but it's here in practice is already present in Compiler. You can invoke Compiler with an argument that says /compile and the name of the file. It will automatically load your project, compile it, and produce an output. So you can operate in CCD. At the moment, you need like a Windows Docker or a Windows virtual machine to implement the step because Compiler is based only on Windows. So the library works on Windows, Linux, and so on, but this tool itself is a tool for Windows. So you need like a Docker machine or a virtual machine like with Vagrant, for example, and you can invoke Compiler passing the last commit of the project file. It will generate for you the Vivado, and one of the flag is if you want that it compile or only generate the HLS and the TCL file. So you can choose if just pre-compile. So the flag are compile or pre-compile. If you execute with pre-compile, it convert the SGF file, that is the compile file, in a series of TCL script and VHDL or C++ file. And you can then invoke you can source the build script to build the Vivado on a second step. For example, for our automatic test, we start from a repository with the test. We call compiler in a Windows Vagrant machine in precompile. We get the output and then we pass the step to the next Docker, Vivado Docker that is based on Linux that compile, and then we check the output. I hope it's enough.
yeah, it was very clear. Thank you. Is there any plan to support Linux in the future? Or?
It's planned for support. It's planned to separate the compiling core of compiler from the UI, because the UI can at the moment work only on Windows and would be quite complex to make it working on Linux because it relies on libraries that is based on DirectX and so on. But the compiling part, that means that if you don't need to modify the design, you just need to compile. It's written in CoreNet, and CoreNet works on Linux. So, but at the moment, it's just a solution altogether. We need to split it, but we want to do it also for us because it's complex to manage the Docker Windows to make the compiling. And so it's planned to separate the compiler like it's made on Vivado. You know that it is the XST tool that compile, and the Vivado is just the graphical tool. We want to do the same. Maybe in a next future could be possible that we decided to migrate like to a web-based platform, and a web-based platform obviously can work on any operation system.
Thanks a lot.
But the next step will be to separate the core from the graphical user interface, and the core can run on Linux.
Sorry. Any other questions? I have a couple of questions. Say that one wants to use this like in a physics, high energy physics experiment, or where you need to match a Monte Carlo simulation. Do you provide like source code or models of all those filters? Say that I'm using it for a trigger and I want to integrate in a...
Okay, so it's the opposite of what it's difficult to make this I think inside a simulation of Monte Carlo. It's I think better the opposite. That is, you generate a file like a CSV or a binary file. We can load in the stimulus of the simulation and then execute the simulation, because the simulation it's the simulation of VHDL code. It's also simulate the timing of design. Okay, so the fact that you provide one data now and one data after one clock cycle, and we produce the data after 12 clock cycle, and so on. And when you make a complex design, you are making like a block diagram that merge multiple algorithms together. So it's not enough to provide just a C++ code for each one and put all together, because also the timing in a FPGA, timing not meaning just closing the timing of the FPGA, but also the how the data are distributed inside the pipeline is important. So making an FPGA simulation just in C, it's something that can maybe hide some issues. So it's better that you provide to the tool, like it's done now, a file that represents your physical detector, and we execute on that physical detector the output, and then you can save the output in a file and continue the simulation maybe of the steps that are later, that are after.
Okay, thank you. I think we are out of time, so thank you again, Luca and Andrea.
Thank you. Thank you all.
Hopefully see you at CERN in May.
Yeah, for
Okay.
sure. See you later.
So bye, everyone.
Thank
Bye.
you. Thank you.